So we're starting with a true false, we usually do. And I'll just say this again as a reminder. You're not being graded on participation or correctness. I'm just doing this to get a sense of how you guys are doing. So it benefits you to put something down. I won't know if you got it wrong. I'll just know how many people got it wrong. So yeah. And then if I know people are getting it wrong, I'll explain it more. But out of the way, I'm talking about A here for question 1. So enolates are formed under acidic conditions. Is this true or false? I'm gonna end it in a second. So 3 of you said it's true and 2 of you said it's false. Probably saw more stuff related to this today, but remember this, that's not an oxygen. This is an enolate. And you form these from like ketones, aldehydes, other carbonyl structures that has a negative charge on it. And if something has a negative charge, it typically is formed by adding some sort of base or like having some sort of nucleophile attacking something. So that's the case here. Like you would be adding a base to a carbonyl to make an enolate. So this question was false because it says acidic conditions. And if you added an acid to a ketone like this, I'll just say like H plus, you wouldn't get an enolate, but you would get an enol like this. So the conditions you use are really important. They'll lead to different products, and then those things might react a little differently. So just recognize the difference between acid and base and what they lead to. Okay, next one. Bases such as sodium hydroxide and sodium ethoxide cannot fully deprotonate aldehyde alpha protons. And something that came up in class last Thursday, or consider the pKa of those bases and the pKa of an alpha proton. That might help you figure this out. Give it like 15 or so more seconds. Three of you said it's true and 2 said it's false. This is like an example of the kind of reaction that you'd be considering to think about this question. You're adding hydroxide to deprotonate an alpha proton from an aldehyde to make it into an enolate. And when you're trying to figure out like how well this reaction will work, you should consider the pKa of the acids on both sides. So like we're looking at this proton on the left side of the reaction, and we're looking at water as the acid on the right side. What's the pKa of water? This is a value you should have memorized. Like a rough whole number. So I'm going too fast, but the pK for water is about 16. If you don't notice yet, just maybe use flashcards, practice it, because it is a number you're expected to know. What about the alpha proton for an aldehyde? This is a pK value you saw in class last Thursday that you were told to remember. And if you're not sure, something to use flashcards for, that should help with memorization, because it is kind of just memorization, but it's about 10 or 11. And a lower means stronger acid. And typically, reactions like to go from more reactive to less reactive, because then they're going towards stability, they're becoming more stable. So if you have a reaction that can go in both directions, it's going to prefer going in the direction that leads to the less reactive one, the more stable side, which means you'd want to go towards the side with a higher pK because that's a weaker acid, so it's less reactive. So that is to say that like this side of, oh, wait, did I flip that? Oh, the pK is not that high. If you ever notice I'm doing something wrong, you can tell me. But if you didn't know the number, that's fair too. But this was supposed to be 20. That's why that was flipped. pK value for an alpha proton on an aldehyde is about 20. So that's the weaker acid side. That's a weaker acid than water. So this side is going to be preferred in this reaction, which means you can't really make much enolate since it's going to want to stick around on the left side. So kind of long-winded explanation, but that is why this was true. And I know the majority of you got that correct, but not many people answered. So people who put the wrong answer, that is why. That is the kind of thought process you could have. Next one is C. And it is if an unknown compound is treated with excess hydroxide and iodine and yields yellow precipitate methyl ketone as part of the structure. No, that's very specific, but it was discussed all briefly in class. So I'm going to erase this stuff. And just so you're aware, something like this would be considered a methyl ketone. I mean, both sides are methyl, so I guess I'll put another carbon here. But as long as there's at least one methyl group alpha to the ketone, it's a methyl ketone. I'm going to go ahead and end the call. So those of you who answered are split. And I don't know how much details for this you have to know, so I'll try not to take too much time, but since you guys are split, I will discuss it. So if you're adding excess hydroxide and iodine to a structure like this, the sodium hydroxide is just a base. And we were just discussing that a few minutes ago. You add bases to structures like this to help form an enolate. So that's the purpose of the base. And like you could form a little bit of this enolate, and then that enolate will react with the iodine because enolates are nucleophiles. I2 is an electrophile. And then you put an iodine on the alpha position. Oh, that's not right. Like this. Put an iodine on the alpha position. But there are still 2 hydrogens here on the alpha spot on the right. And we're adding excess hydroxide so we can convert both of these hydrogens into enolates, and then those can react with iodine. And basically, like after that happening 2 more times and replacing those hydrogens with iodine, like you've replaced all of the hydrogens with iodine, you have a CI3. And I don't know if this is a detail you really have to know, but this, like, that circle, this could be like, it's kind of like a leaving group. Like we were in chapter 21, you saw stuff like carboxylic acids and esters and acid halides, all of those functional groups. Like you had a leaving group, you add a nucleophile and kick out the leaving group. That was what all of those reactions were doing. And you can treat this group as a leaving group, basically. And we still have hydroxide, so that's going to attack the carbonyl carbon. And like it's going to do the whole mechanism. I won't go through the whole thing because that would take too long, but in kind of summary, like you're adding the hydroxide, you're kicking out the leaving group. And then you form a carboxylic acid, and you kicked this out, and then that'll take the proton. And it's a very long process, but in the end, you form, circle out a different color. You form this as a byproduct because it got protonated. This is iodoform, and in solutions, it would precipitate and it would be yellow. So that's what it's referring to. So again, I honestly am not sure how many of these details for this process you have to know, but you should know that if you add hydroxide and I2 to a methyl ketone, you'll get a yellow precipitate. And all this is why, because it replaces all the alpha hydrogens, then you kick out this, and then you form iodoform, which precipitates. And just like as an example of maybe something he could ask, I don't know if this would come up on the test, and if it does, I don't know how exactly, but maybe he could ask, like, if you added these conditions to, say, this structure here, would you form a yellow precipitate? And if you don't know, like, how the yellow precipitate forms or what it indicates, then you wouldn't be able to answer this. Oh, I didn't say the answer. This is true. I kind of explained why it was true, but it's true. So, like, I'll pose this question to you guys now that I explained it. If you had this ketone down here circled in red, and you added those hydroxide and I2 to it, are we going to form iodoform? Are we going to get a yellow precipitate from this structure? Remember, I emphasized the methyl group here. It's a methyl ketone that it indicates the presence of. So without a methyl group, alpha to the ketone, none of this stuff is going to happen. I mean, you can still add iodine, but you're not going to form the precipitate. And there is no methyl group next to the ketone in this structure. So you wouldn't get a precipitate there. So I'm not saying he'd ask a question like that, but it is a possibility, I suppose. It's something I came up with. He probably could too. So just be aware of this concept and be prepared for questions about it. Okay, last question is D. A reaction is considered base catalyzed if the base is consumed during the reaction. And we've talked about what a catalyst is, like what it does and like definitions of it. So consider that for this question. I'm gonna end it in like 5 or so seconds. Okay. So most of you who submitted got it correct. It is false because remember, catalyst is regenerated reaction. That's like what makes it a catalyst, because then it can go on to catalyze another reaction and then it's regenerated and it catalyzes another one. Like you can use it over and over and over. But this is saying it's base catalyzed if it's consumed. If it's consumed, it's not a catalyst. So it's false. And just for the sake of completion, it's called a base promoted reaction if the base is catalyzed, or if the base is consumed. Just as a definition. And categorizing reactions like that is a good idea because you're going to see examples of both. Probably did today, you will over the next week or so. Okay, so I'll move on to question 2. This one is asking to identify the hydrogens that can undergo alpha substitution reactions. And can anybody tell me, like, as a general rule, what we're looking for? Like, what hydrogens can do these reactions? Where do we find them?
I don't remember exactly, but it's like the hydrogen that's closest to the carbonyl or something, or on that alpha carbon.
Yeah, and what's the alpha carbon? Like, where is it?
It'd be the second position after the carbonyl carbon.
Yeah, so like if you're looking at this carbonyl, that's carbon 1, and then these two, you could say are number 2. They're right next to the carbonyl carbon, so those are both alpha. And then the hydrogens on those carbons are the alpha hydrogens that you're interested in for these reactions. So there's 3 of them on the carbon on the left here. And then there's 2 on this one. And then we have an ester, and this spot is alpha to it, so this hydrogen is also 1. So in total, there were 6 alpha hydrogens that could do reactions in this structure. Okay, I'll just ask the question about this one. How many hydrogens or how many alpha hydrogens are there in this structure that I've circled? You don't.
Only 2.
So yeah, those are the clear ones because they're both alpha to the ketone. Amines, like it is a functional group, but there's nothing special about the alpha hydrogens next to an amine. It doesn't really affect it in any way. But nitriles are a bit special, even though they're not carbonyls. Remember, like we talked about a few chapters ago, how nitriles and carbonyls are fairly similar. Like a carbonyl is a double bond to an oxygen, and a nitrile is a triple bond to a nitrogen. And like they both have a dipole from the carbon pointing to some electronegative atom. And sometimes they can do similar reactions. And if you think about it, like what makes the alpha spots on ketones and other carbonyls special is like the fact that when you form the enolate, it has that resonance form with the carbonyl because there's a negative charge right next to a double bond. And that resonance stabilizes it, so it made it possible to form the enolate in the first place. And like if we look at an enolate alpha to a nitrile, it's the same idea. There's a negative charge next to a triple bond, so you can push it towards the nitrile and draw a resonance form. And that also stabilizes the enolate, so it's possible to form that. And this is all to say, like the alpha hydrogens, alpha to a nitrile, are basically the same as alpha to carbonyls. So we would also want to consider this one because it's alpha to the nitrile. So just don't forget that nitriles are like an oddball in this chapter, but they are still important to remember. And what about this last one? How many alpha hydrogens do we have there?
I don't think there's any.
That's correct. There aren't any because there's a bunch of methyl groups. This is alpha and this is alpha. There's no hydrogens there. So yeah, just get used to identifying alpha spots quickly because you'll be doing a lot of reactions at that position. If there were, go ahead.
The first one had it was 5.
There are 6 because there's 3 here on the left.
Oh, that's what I missed.
Yeah, one of them was kind of covered. It's okay.
Okay, thank you.
And if there are any other questions about clarification or just an explanation, feel free to ask. Otherwise, I'm going to keep going. Here's an acid ranking question, like ranking the strength of these acids. And for these, like this is a place where knowing pKa values is really important, because I'm assuming you've seen it already, unless he's changed his tests. He likes asking questions like this on every single exam, so you should expect it. And you do have general values for all of these hydrogens, like in this first structure. I already told you hydrogen's alpha to a ketone or an aldehyde, the value is roughly 20. That came up earlier. What about a hydrogen like this that's alpha to 2 carbonyls? Can anybody recall what the value was for that? If not, it's cool. Just put it on a flashcard, memorize it, because this will probably come up. This one's about 10 or 11, somewhere around there, when it's alpha to 2 carbonyls. What about in alcohol? Hydrogen. This is an older one, but you should still remember it.
16.
What about the last one? Carboxylic acid here.
10 again.
Not 10, a little lower, because it's a strong acid.
Like a lot lower, like 4 or
Yeah, the number for this to have in mind is 5, but yeah, it's pretty low. So yeah, these are some, not all, of the pKa values you should know, but that's what it is for this question. And remember, lower pKa means stronger acid. So we're saying 1 is the most acidic, 4 is the least acidic. So once you have the pKa values in mind, you can just go from lowest to highest pK. So like this is 1 and 2, 3, and 4. That's how you would rank these, because it went from low to high pK. Okay. And we'll have a similar process for the next one. So there's an alcohol in the top. pK is about 16 for that. We have a hydrogen here, alpha to 2 carbonyls. pK for that is about 10. This one is alpha to 1 carbonyl, that's a ketone. So pK is about 20. What should the pK be for this last one though? We didn't see an example of this earlier.
does it even have a pKa?
It does, but it's like, is there anything special about it?
Not really.
Yeah, it's just a regular carbon-hydrogen bond. So like it's very, very, very weak. It has a very high pK value. You should just have like this idea that it's like between 50 and 60 in mind. It's very high. It's not much of an acid at all, but that is the number to have in mind. And again, go from low to high pK. So this is 1, this is 2, 3, and 4. And last one, this is alpha to 1 ketone, so that's 20. Again, this one is alpha to 2 ketones, that's about 10. This is alpha to an ester. That's what this functional group is. It's an ester, not a ketone or an aldehyde. And it sucks, but they have separate pKa values from ketones and aldehydes. So this one is about 25. It's a little higher than ketones and aldehydes. And this is the same value for other carbonyls like esters, nitriles, amides, like the other carbonyls besides ketones and aldehydes. And then that last one, you don't have a pK value that you have to know for this, and I don't know what the pK would be for this exact one, but it's alpha to free carbonyls. It's alpha to this, and this one. And the more carbonyls that are alpha to a hydrogen, the more acidic it is, because that would mean like if you drew the conjugate base, it would have more resonance forms. So I'll just put that as a note. So I don't have a value for the pK, but that should be the strongest acid because it has a lot of alpha carbonyls. And then this should be 2, this should be 3, and that should be 4. So I guess a takeaway from this, if you don't know your pK values yet, I would get on that and just make some flashcards, float through them a couple times. It'll probably help you get it down. Okay. Move on. This question is saying, how many times could the following compounds react if excess bromine was added under acidic conditions? And it's saying like how many times could they react? So it's basically asking like how many alpha hydrogens are there? Because that is what limits how many times it could react if you added an excess of the reagents. So how many alpha hydrogens are on this structure on the left?
6.
There's 3 on both sides. How many in this one?
I think that one would be 8.
Because there's 3 here, 3 here, and 2 here, so 8 total. This was 3 and 3. And what about the last one?
Just 1.
Just 1 here. So pretty straightforward, I think. But if there are any questions, like feel free to ask. This is just another kind of practice. Get used to identifying these alpha spots. Okay, I'll move on. If there are questions, I'll go back. I don't know if he talked about this more today, but he did bring up this mechanism last week, and it was something that I was expected to know for exams, even though I don't think he emphasized it a lot last week. So I'm gonna practice it here. This is something that you can do in any context. If you have a carboxylic acid beta to another carbonyl, so like if we're looking at this carboxylic acid I've circled, this is alpha and this is beta. So the carboxylic acid is beta to the other one. And basically, if you heat a structure like this, you lose carbon dioxide. You lose one of the carboxylic acids as carbon dioxide. And there's a mechanism for this we're going to go over. The first thing I would do if I was given a structure like this is I would redraw it because it's kind of hard to draw the mechanism with the structure as it's shown here. It's just kind of hard to visualize and show it. So I didn't do anything here. I just redrew the structure. Nothing changed, no electrons moved around. And now keep in mind, like we're trying to lose one of these as carbon dioxide. So it's good to like look for carbon dioxide in the structure. That might help you figure out how the mechanism will go. And like this part I have circled in red is carbon and 2 oxygen. So that could be carbon dioxide. So basically, like if you recognize that, then you can think, how am I going to form that? And then how do I kick it out? That's like what the mechanism is going to be doing. And most of it happens in one step. The carbonyl that's sticking around is going to take the hydrogen from the carboxylic acid, and then those electrons will be pushed down to form another carbon-oxygen double bond. So now we have CO2, and we just have to lose it by breaking this other carbon-carbon bond. So then the carbon dioxide is leaving. That's what we lost. And after you do all of that, what you form is an enol. And remember, enols can do tautomerization. They have an equilibrium with the carbonyl form. So that's what's going to happen next. It's just going to do tautomerization and go back to the carboxylic acid form. So it's pretty short. It's 2 steps free if you count redrawing the structure, but it is something that I was expected to know. So unless he tells you otherwise, I'm assuming you also should be familiar with this mechanism. And I want to emphasize, like, this can happen with any carbonyl beta to carboxylic acid. So it could be a ketone, an aldehyde, an ester, another carboxylic acid like here, amide, like it could be any carbonyl beta to a carboxylic acid. And he might not make it super obvious that that's what's happening. Like maybe he would give you a structure like this. And at first glance, like unless you're looking for it, that might not pop out to you. But if you are looking at this ketone, this is alpha and the carboxylic acid is beta to it. So if you heated it, you could lose this as carbon dioxide in this mechanism. So just one of many potential examples of this reaction happening. And there's a name for this too, called decarboxylation. So you should also know that. Okay. Are there any questions about this before I move on? This is short, but it's tricky. So if you have anything, please ask. It's important to be comfortable with these. Okay. Go back if you do have a question or one comes to mind. Right here we have an alcohol and we're adding sodium hydride and then we're adding ethyl chloride. This is actually an old reaction, but it'll be familiar or it'll be similar to the next couple. What is the first step going to do with the sodium hydride? What's that going to do to the structure? And if you're not sure of that, what is sodium hydride? Like, what should that behave as?
A base.
Yeah, because it's just H minus. That can be a nucleophile or a base. It's going to be a nucleophile, or it's going to be a base here. And an alcohol is an acid. So it's going to do an acid-base reaction. It's going to form an alkoxide. And then we're adding ethyl chloride. So we have alkoxide, which is a nucleophile. We have an alkyl chloride, which is an electrophile. And how are these two going to react with each other? Like, they're going to have a reaction, but like, what kind of mechanism is happening when the nucleophile attacks this electrophile? It looks like this. Like, what would we call this? Yeah, the chlorine leaves when the nucleophile attacks. But what mechanism from 112A is this where the nucleophile attacks and the leaving group leaves at the same time? Yeah, it's SN2. And this forms an ether. So this isn't a new reaction. This is and synthesis. You add a base to an alcohol, and then you add something with a leaving group, and you form an ether through an SN2 mechanism. And the next couple of reactions are going to be fairly similar, so that's why I brought this up. Here we have a ketone, and in the first step, we're adding sodium hydride again. So again, that's going to be a base. This time though, where is the acid? Like, what is the hydride going to react with?
Is it gonna be the carbon this time?
Which carbon?
The carbonyl one,
Oh,
or just
that
the oxygen?
if it's acting as a base, it's going to want to take a proton, right? It's going to want a hydrogen. So where are there hydrogens in the structure?
The alpha position.
Yep. And those protons are relatively acidic, so it will actually want to react with these, and that will form an enolate. And I'm actually going to draw it on the right side, but it's the same idea because it's symmetrical. You get an enolate, just like the alkoxide was nucleophile. Enolates are good nucleophiles. And we're adding ethyl chloride again. And again, it's going to do an SN2 attack. It's going to add that ethyl group to the alpha position. So this is the product you get. And I'm just color coding it to show what we added. We added it to the alpha spot. It was an ethyl with a leaving group. So we added an ethyl group to the alpha spot as the final product. And I didn't ask you, but remember, this is an SN2 mechanism. So remember that it doesn't work with tertiary leaving groups. So that's just something to always be on the lookout for. It might be an issue. It might stop a reaction from working. It worked fine here because this is primary, but if it's tertiary, it won't work. So always be on the lookout for that. Okay, next one, we have another ketone. We're adding NaNH2. This is just another strong base. It's a very strong base, so just be aware, like it won't always be sodium hydride on a test. You can see this too. That's going to help us form an enolate. But which enolate is going to form? We have two potential ones. It could form here or here. Why the left side? Did Okuda say something about it today? Because I haven't watched the recording yet. If he did, like I could have the wrong idea, but it is less hindered. That's true. So well, I won't go into detail about it because I'm not sure if he talked about it, but it's less hindered. So like you could form that faster. But if you draw the enolate from the right side, like this is the enolate form, but remember we can draw a resonance form by pushing negative charge towards the oxygen. And then you get this alkene with the negative oxygen. And I'll just draw the other alkene form over here. What could we say about the stability of these two? Like which one is more stable, the blue one or the red one? Consider the alkene, like this and this. What determines alkene stability? Blue, yeah, because it's more substituted, so it's more stable. So the blue one is more substituted, so it's more stable. And again, like if he brought this up in class, or if he brought up the idea of controlling conditions to determine like if you form the more stable alkene or not, then go with what he said, but I don't know what was covered in class yet, so I'm not sure. So I'm just going to operate on the assumption he didn't talk about it, and you can just assume, unless he said otherwise, that the more substituted alkene, which is more stable, is going to be the one that you use to lead to the final product. So that's the enolate we're going to use, the blue one. So it's a secondary substrate. So that works fine for SN2. It's going to, oh, not like that, actually. It's going to be the enolate that does the attack, but it is going to work. So we just add an isopropyl group to the alpha spot. I'm going to erase the screen and move on to the next one. This is just another strong base or enolate, just like sodium hydride and NaNH2 were. It's just another example. And I'm gonna skip showing like the acid-base reaction to form the enolate. I'll just say like you're gonna form one at the alpha position. That's the intermediate you'd get. But this is tertiary. Remember, tertiary leaving groups don't work with SN2. So you could probably put no reaction. That might be safe because it's not doing what you want it to do. But if you have a good nucleophile and a tertiary substrate, you're typically going to be doing an E2 reaction. So this is what would happen. You get an alkene. And then you get the same thing you started with. I'll just redraw that too. But this is the biggest change. Okay. Next, we're adding hydride to an ester, and then we're adding methyl bromide. Hydride's still a base, and we have an acidic proton on the alpha spot. So hydride's going to take that and form an enolate, just like it did with the ketones earlier. And then we're adding a methyl bromide, which is perfectly fine for SN2 mechanisms. So it's just going to do this attack like we have been in the past. And we're putting a methyl group on the alpha spot. However, for the next one, like it looks very similar. We have the same conditions, adding sodium hydride and then methyl bromide, and we have a pretty similar looking structure. The only difference is this is a carboxylic acid instead of an ester. Are we going to get the same product we got in the last one, adding a methyl group here?
No,
Why not?
I don't know.
Consider the relative strengths of the acids that are here. Like, would you say this hydrogen at the alpha spot is more acidic than this hydrogen in the carboxylic acid?
No, the carboxylic acid one is a stronger acid.
Because this has a pK of about 5. I think the pK for this alpha proton would be about 25. So this has a lower pK, it's a stronger acid. So that's going to be the hydrogen that the hydride takes, not the alpha proton. So just as a general thing to keep in mind, a base will always take the most acidic. If there's multiple, then it's going to go for the most acidic one. And we have kind of been doing that this whole time. We just didn't think about it as much. Because like in this structure up here, the alpha hydrogens weren't the only hydrogens. We also had hydrogens here. But remember these, there's nothing special about them. They're just carbon-hydrogen bonds. They have a pK of like 50. So they're weaker acids and we ignored them. We just looked at the alpha spot. But it was the same idea. We took the most acidic proton. And here we're going to take it from the carboxylic acid. So that will lead to a carboxylate forming instead of an enolate, since we took the carboxylic acid's proton. And then it's going to do the same kind of attack. It's going to attack the methyl bromide. And this is going to lead to an ester forming. Very different product, even though the structures looked similar, because it was a carboxylic acid that had a stronger proton. So just keep an eye out for kind of misdirects like this, where it looks like it'll do one kind of reaction, but it does something else because of maybe a stronger acid or something like that. Okay. I think I'm just gonna go through these so I don't go too far over the time. So we're starting with an ester here. We're adding H3O plus to it. Remember from before, if you have H3O plus, that means that there's also water. You can't have H3O plus without water. They come together. So we're basically adding water and acid to the ester. And remember, if you add water and an acid catalyst or a base catalyst to a carboxylic acid derivative, you get a carboxylic acid. We're doing hydrolysis. You also get an alcohol here, but the carboxylic acid is the main thing you're looking for, probably. So just a bit of review there. So, and that's a bit related to some of the reactions we'll be looking at in a minute. For the next one, we're adding one equivalent of a base in the first step. That's what this is. This is just a base. And just like all the other reactions today, the purpose of the base is to form an enolate. We're going to form it here because this spot is alpha to 2 carbonyls. That's a very acidic proton that was there. So that's where the base attacks. Since it's so acidic, you form this enolate. And then in the second step, we're adding ethyl chloride. So just like all the times before, we're doing an SN2 reaction, and we're adding an alkyl group to that alpha spot, alpha to both of the esters. And this is where this reaction stops because I don't have any extra steps. I just put the base and then the alkyl chloride. But with a structure like this, it can go further, as we'll see on the next one. And I want to emphasize that the equivalents here are important, and Okuda will put them on the exam. So like we're adding one equivalent because we only want to form one enolate. We don't want to like take all the protons from it. And then you're putting one equivalent of the alkyl halide to only add like one ethyl group here. And this was a typo on the next one. I meant to put one equivalent. So we're gonna like assume that I put that. If you worked through it, assuming like I meant excess because I didn't put it, that's my bad, but this is what I meant for it to be like. So again, we're adding one equivalent of base. That's going to form an enolate just like it did before. And then we add an alkyl halide. This is a primary alkyl halide, so it works fine for SN2. And we're going to do that attack. That leads to this structure. And then in the third step, now we have an extra step. We add acid and heat. So the purpose of the acid is the same purpose this acid in the first reaction here did. We have 2 esters. We're adding acid and water. So this is just going to do hydrolysis on those 2 esters. It's going to turn them into carboxylic acids. And then once you do hydrolysis, you might notice that if we look at this carboxylic acid on the right, this is alpha, and the other carboxylic acid is beta to it, and we're heating the structure. We talked about a mechanism for this earlier. I'm not going to go over it again, but you could practice it with this structure. But if you have a carboxylic acid beta to any of your carbonyl and you heat it, then you're doing decarboxylation. So we're going to lose one of the carboxylic acids as carbon dioxide. And this would be the final product after you lose the carbon dioxide. That's what you get. In this process of having two esters beta to each other, and then adding a base and an alkyl halide, and then you had acid and heat, it has a name. It's called malonic ester synthesis, or ME synthesis. And every single time you do this, no matter what you're adding, like in the second step with the alkyl halide, no matter what you're adding, the product is going to have a general form. This part I have circled in blue and drawn in blue. I'll draw it over here. By itself, like this is acetic acid. It's a common carboxylic acid you might know the name of. And we just formed a substituted acetic acid. We added stuff here to the alpha position. And that's always going to be what the product looks like. It's always going to give a substituted acetic acid. So if you recognize that that's always going to be what the product looks like, then you can kind of skip drawing all these intermediates and just jump straight to the end where you have the acetic acid and then you add whatever it is that you added to the alpha spot. And I'll go over thinking about it like that more on the next one, and maybe a little more on another worksheet, but that's the general idea of this. This next one, we have an ester, but over here we have a ketone instead of an ever ester. And what we're doing is fairly similar. We're adding a base and then an alkyl halide and an acid. So enolate forms from the first step, and then it attacks the alkyl halide in the second step. It's the same idea as before. And then we're adding acid and heat. The acid, again, is going to do hydrolysis, but this time it's only going to affect the ester. It's not going to touch the ketone because you don't do hydrolysis with ketones. So ketone is left as is. The ester is turned into a carboxylic acid. And again, if you're looking at the ketone, this is alpha, that's beta. So the carboxylic acid is beta to the ketone. We're heating it so we can do decarboxylation. Remember, carboxylation can happen when any carbonyl is beta to carboxylic acid. Ketone, aldehyde, ester, another carboxylic acid, it doesn't matter as long as you have something like this. So that's what's going to happen here. You're going to lose carbon dioxide. And then this is your product. And this is a little different from malonic ester synthesis. This is called acetoacetic ester synthesis, or AE. And you should know these names. And just like malonic ester gave a characteristic product, this will too. This part circled in blue is acetone. It's just a free carbon ketone. Might be familiar with it. And we just added something to the alpha position. It was whatever you added in the second step. You add that to the alpha position. So this gives a substituted system. Just like the last one gave a substituted acetic acid. It's a characteristic product. If you recognize that, you can just jump straight to the product. And that's actually what I'm going to do on the next one. I am not going to go through all of the intermediates. I'm just going to go straight to the product. But this time we have 5 steps. So we're adding base, and then we add one thing, and then we add another base, because there's 2 protons here. So we can form 2 enolates. So we form one enolate, we add that thing in step 2. We form another enolate, and we add this. And then we do the decarboxylation and all of that stuff. And in the end, since there's 2 esters here, this is malonic ester synthesis. So the product is going to be a substituted acetic acid, which means like you can start by drawing this. You know this is going to be a part of the structure. And then we added an ethyl group, so that's from step 2. And then we added a propyl group in step 4. So there's the propyl group, and that's the product. It's an acetic acid with an ethyl group and a propyl group on the alpha spot. And then you don't have to draw all those intermediates and spend several minutes on it. It would take like 1, maybe 2 minutes when you look at it this way. So it's a lot faster. Okay. I'm gonna go ahead and erase this and move on to the last one. And I'll try to be brief on that one as well. Even though I'm going fast, you can stop me with questions if you have them, because that's what I'm here for. For the last one, it's a synthesis. We're starting with an ester, and we converted the ester to an amine, like the carbon with the ester here is this same carbon where the amine is. So that's transformation we're doing. And we also added carbons. We added all of this. And it's good to take note of where you're adding carbons, because that might affect like what reaction you used to add it. We put them here, where I'm circling in red, which is the same spot in the starting material. And that is alpha to the ester. So it would make sense if we were using some of the reactions we've been looking at lately, where we add stuff to alpha spots to add those carbons. So that's going to be how we start this, actually. We're going to add that alkyl chain the same way we have all day today. It's a 2-step process. You add a base. It doesn't really matter what the base is. I'm just going to use sodium hydride. And then in the second step, you add whatever alkyl group you're trying to add. Here, we're trying to add that cyclopropyl and another carbon. So this is what it should look like. That's what we're adding. And then, so we've added the alkyl group. Now we want to convert the ester to an amine. We can move towards that by converting the ester into an amide. We can't convert it into an amine in one step. But if we add an amine to it and we heat it up, that will convert the ester to an amide with a carbonyl. And then we still have this that we added. And last, we can convert the amide to an amine by reducing it. This isn't the only way to do this, probably, like most synthesis problems, but I think it's the most straightforward way that I could come up with. So that is the worksheet. If you have any questions about this synthesis or anything else I talked about today or in class in general, feel free to ask. If not,
I wanted to ask, are you going to post another worksheet with a bunch of synthesis pathway problems? For the
yeah, if I don't do a review session, which I'm feeling pretty busy this week, so I'm probably not going to, I'll post some synthesis problems to practice.
Will you post the key this time? Because last time I had no idea how to do any of them.
So if you are struggling, you can send me what you have, or even if you don't have anything, you could just ask me for some hints and I'll give you some. But for these, I don't want to post an answer key because if I do, I think people will just like look at the key and then like it does help, but I think it helps more to work through it on your own and struggle with it. And if you get stuck, then you get some help and then you can work through it a little bit still.
Okay.
So
Yeah, no, I get you.
just
I just
reach out to me if you get stuck. That's what
okay,
I'm here
I got
for.
you. I usually do it like the night before the exam. So I mean, if you're still up around that time, then yeah, I'll send it over.
Yeah,
Just in case.
I'll try to be available.
Okay, sounds good. Thank you so much.
Hmm.
All right, see you next week.
See ya.